Every matrix secretly contains two worlds, one that describes everything it can produce, and another that describes everything it destroys. They're called the column space and the kernel, and they tell us almost everything about what a specific matrix does. Hey, I'm Oliver, a computer science student and tutor. I used to get lost in linear algebra because I did not understand the fundamentals as well as I thought I did. Now I make short concept overview videos in the hope that I can make some of these fundamentals more accessible and understandable. In this one, we will take a closer look at what the column space and the kernel tell us about a matrix. First, we'll change the perspective we have on matrices. So for a matrix A, which has n rows and m columns, we can define this as a function f. Our input is a vector coming from Rm, so a vector of size m with real numbers, and our output is a vector of size n. The function f, which is just a multiplication of its input, like this, ends up having an output in this. And in fact, this is a linear transformation, seeing as we, through our matrix multiplication, only have scalar multiplications and additions. To make this a bit more concrete, I've created a little example. Here, we have a 2x2 matrix, which describes a transformation that we will get into now. We've also defined our v as a variable vector, so it can be any vector, and we've just entered these variables here, so that when we do this multiplication, which is the function that a describes, and we solve this, we see that this is the output. So what the function a, this linear function a, describes is swapping these two values. Before we had v1 and then v2, now it's v2 and then v1, and also scaling this first entry, which used to be the second, multiplying it by 2. So this matrix multiplication, which can be interpreted as a linear function, describes this linear function, going from v1, v2 to 2v2, v1. Looking at a specific example, we can look at this vector v here, which is 3 and 1, plugging in those values in the output that we've derived previously, we get the vector 2, 3. So the input is this vector here, or also this point, and applying a, so performing the function a, moves it from here up here. And now every single point can be taken and have this operation applied, and we land somewhere in this space. And where exactly we can land brings us to our column space. Coming back to the image we had at the beginning, we see here that I've sketched out some shapes, and these represent the vector space we're moving in. So in our previous example, v would have been rm, and w would have been rn. And then this linear function L would have been rf. Now the multiplication, which I've just shown you, would, for example, be taking a point in our rm, applying the multiplication L, and then landing somewhere in our space W, so Rn. Now, we can land anywhere inside this vector space, but we can't land outside. However, there's also other areas we cannot reach. So in blue, I have sketched in all the points that can be reached, but there are points which are in our W, but our linear operation L does not reach. And this area is then called the image, or also the column space. The column space is every reachable point in our codomain, so our output vector space, assuming we take every vector from our domain, so our input space. So it represents everything that our matrix can produce. And if it's a point outside our column space, we can never reach it with this linear operation. Formally, the definition of column space is that for a matrix, which is composed of these rows A1, which have length n, and there are m many of them, it is just our span of all of these vectors. So our column space is the span of all the columns of A. And that is why it's called column space. And if you remember from my previous video, this is the definition of span. So every point that's reachable through linear combination of our input vectors. There's another concept called the rank, which is related to the column space. And it is the dimension of our column space, meaning the rank tells us how many unique directions our column space has, which is equivalent in the definition as saying it is equal to the number of linearly independent columns. So, however many of these vectors are linearly independent is equivalent to the rank of A. We also frequently, instead of writing the span like this, just write it as the span of A, telling us that it's the span of all our columns of A. So written as above, but in a shorter format. Now looking back at our example of the matrix A, its column space would be written like this. Span of A, and then this is the linear combination of its columns with variable lambda 1 and lambda 2. Now I will not go into specifically solving this, but seeing as these two are linearly independent and vectors of length 2, this entire span is the entire R2. And from our previous video, we also know that the dimension of this, so the span as well as this R2, is 2. So we can say that the rank of this matrix is 2. And if, for example, we turn this 2 into a 0, then this vector just becomes the 0 vector, so it doesn't contribute to this linear combination. We just have this component here, so we would only have one unique direction in this span. So we would no longer have our R2, but a different vector space. And considering we just have one direction, it means that our matrix has rank 1. To summarize, if this 2 were a 0, the rank of this matrix were 1. A small note on this is that you can use, for example, Gaussian elimination to help find the rank of a matrix by bringing it into row echelon form, which would be the staircase format where underneath it, so where this 1, for example, is, we would have zeros and above it non-zeros. And this format can go on for longer matrices. Anyways, I made a video on Gaussian elimination. I suggest you check it out if you want to learn more about this. Gaussian elimination helps you find the rank by counting the number of steps in the row echelon form. Lastly, we'll take a look at the kernel. The kernel, written here as KER of L, is all our vectors in our domain, so our input space, that when we apply L to this, we land in the origin. And this is the origin of our vector space W, the codomain. And the kernel describes everything that our matrix destroys, so that no matter where we start from our kernel, applying L on this brings us to our point 0, so no information is preserved. So formally, for a matrix A with n rows and m columns, so with a domain Rm and a codomain Rn, the kernel is described as every vector in our domain, so our input space, that when applying this operation A, so matrix multiplication with our input vector, that we land in our output space, so our codomain, in the 0 vector. Now here I have two examples. Once our matrix is this one here, which is the identity matrix, where we have 1s in our diagonal and else just zeros. And this is called the identity because multiplying it with anything just produces it again. So multiplying our v, which would be this vector here, times our a, which would be this vector here, we receive just this v again, since we're multiplying with the identity, and setting this to 0, which is our condition for being inside the kernel, yields us that this v vector must have been equal to 0. So v1 and v2 must have been equal to 0. This means that for a vector v to be in the kernel, it needs to fulfill this condition, and this condition is only fulfilled when v1 and v2 are 0. Meaning that the only element we have in our kernel is the 0 vector, where both v1 and v2 are 0. And this is also considered the trivial kernel, where just the 0 vector is included because the 0 vector is always included. Multiplying any matrix by the 0 vector always yields 0. Now for the second case, I've slightly adjusted this matrix, where now we have a 0 down here instead of a 1. then setting up this condition again for the kernel and doing this matrix multiplication where the first entry stays the same as before because only the first row is used, and that was the same case for up here. And then for the second row, so the second entry, writing 0 because these zeros multiplied with these just equal 0. So we get the condition that this vector must be equal to 0, which is true for the second entry, and for the first entry is true when v1 is 0. So we get that v1 has to be equal to 0 as before. However, now we do not have v2 in this equation. So our v2 can actually be whatever we want. Every single v2 works. This condition is not affected by it. And thus, in our kernel, for the second case, we allow all vectors v that have the form 0 and let's say lambda, where our lambda is any scalar number. So this represents an infinite amount of different vectors that multiplied to this matrix equal to 0. And one can see this because if this vector were to be written on this side here, our multiplication in the first row would multiply like this and multiply 1 with 0 and 0 with lambda. And in the second row, because we already have zeros, it would just multiply to 0 again. So to summarize, for a linear transformation L going from vector space V to W, the column space is every single point reachable through that transformation. Everything outside the column space cannot be reached by applying this linear operation. The kernel, on the other hand, lies within our domain and represents every single point. Applying our linear operation L, it lands us in the origin, so in the 0 vector. Now, the kernel is sometimes also referred to as the null space. So if you hear that term, it is equivalent. And the column space is often written as this IM, meaning the image, which is also equivalent. Now, there is an interesting relationship between the column space and the kernel, and that is formalized in something called the rank nullity theorem. In the next video, we'll see this beautiful connection, where the dimension of the column space and the dimension of the kernel always add up to the number of input variables, so the size of our domain. If you want to keep learning linear algebra, check out my playlist that starts from the basics, or take a look at this video. If you enjoyed this, consider subscribing for more short concept overviews. And as always, thanks for watching.